Hi, so in this short tutorial, I'll be going over the basic logic gates, what they are, how they work, and why they are important in digital electronics. I've included the truth tables, the standard symbols, and explained the functionality of each gate. So let's get started. So logic gates are the fundamental building blocks of digital electronics, performing basic logical functions that are essential for digital logic design. This tutorial covers the common types of logic gates, their truth tables, and practical application. So first off, we have the AND gate. So this is the AND gate, and it only gives 1 at the output when both of the inputs are 1, as shown in the truth table. So we can see that one of the inputs are 0 here, so the output is 0. So we can see both of them are 0 here, so the output is going to be 0. We can see the first one is 1, but the second one is 0, so the output is going to be 0. But in the fourth case, both the input A and B are 1, so as we can see, the output is going to be 1. So only when both of them are 1, it's going to be 1. So it kind of works like multiplication, right? So in multiplication, if we add 0 and 1, then we get 0, right? But if we add 1 and 1, then we actually get 1. And we can see that we have A in the first input and B in the second input. So in the output, right, we get A multiplied by B. So it kind of works like a multiplicator. And the symbol for this logic gate is actually a D. It looks like a D, yeah. So next up, we actually have OR gate. To be more specific, we have two input OR gate. So like the AND gate, we have two inputs here. So one is A and the other one is B. So if you actually look at the truth table, we can see we actually have 0, 0, which is 0. But if even one of the inputs are going to be 1, then we'll actually get 1 as an output. So we can see that we have B as 1 here, but A as 0 here. But that doesn't matter. If one of them is 1, we'll still get 1 as output. So it's the same for the rest of them as well. We have 1 here, 0 here, but that doesn't matter. If even one of them is 1, then we're gonna get 1 as output. And we can see both of them are 1 here. So it's the same for this one as well. Even if both of them are 1, we'll still get 1 as an output. The logic gate looks kind of like a curve shape that points towards the output, right? With two input lines feeding into the feeding from its left. So we have two input lines that's feeding from the left, and we have one output line. So next up, we actually have the NOT gate, also called as an inverter. It takes just one input and flips it. So basically, if you have A, right, it's the output is gonna be A prime. So if you have 0, right, like look at this table, if you have 0, then you'll get 1. If you have 1, then you'll actually get 0. So it basically just flips the input. The NOT gate is a fundamental digital logic gate that performs logical negation, just like we discussed above, outputting the inverse of the input signal. So it is commonly represented in the truth table, and it is essential for various digital logic circuits. So functionality. The NOT gate or inverter, in other words, outputs the opposite of its input signal, right? Like we discussed. And we actually saw the truth table. The symbol for NOT gate is a triangle. We can see that it's a triangle with a little like small circle at the right side. So yeah, that's our NOT gate. So the circle actually indicates the inversion. So then we actually have NAND gate. So NAND is basically an AND gate with a NOT gate right after it. So this looks exactly like the AND gate, right? The only difference being we actually have a small circle right at the end. So this actually indicates inversion. You can tell from the truth table that it's the opposite of AND gate. So in AND gate, right, if one of them, either one of them is 0, then the output is always going to be 0. So we can see it's actually 1. So basically it's the inverse of AND gate, right? So we can, it's the same for the second one. A is 0, B is 1. So we should get 0, right? But no, we actually get 1. So that's the flipped version, the inversion version of AND gate. It's the same for this one as well. We have 1 here as A and 0 here as B. But we still get 1, right? So it's the inversion of AND gate. And at the last one, we have two ones here. So one, one in the A, one in the B. So we are actually supposed to get 1 with the logic of AND gate, but this is actually an AND gate, which is basically the inversion of an AND gate, right? So instead of 1, we actually get the inverted version, which is 0. So we can say an AND gate is basically a fancy way to say an AND gate with inversion. So we actually have the functionality here. The NAND gate is the combination of an AND gate followed by a NOT gate. It outputs the low signal 0 only when both outputs are high, right? We can see that only when both of the inputs are high, we get 0. And for the rest of the cases, it's always going to be 1. Doesn't matter what. And like we discussed, the NAND gate actually resembles exactly like the AND gate with a small addition of a circle at the output. This is output, right? The small addition of a circle right here to indicate the negation or inversion, whatever we want to call it. Then we actually have the NOR gate. NOR gate, like NAND, NOR gate is just like NAND but based on an OR gate. It outputs 1 when both inputs are 0. So even if one input is 1, right, the output goes low. Just like NAND, it is also a universal gate, and you'll often see it used in a memory circuits like latches or simple registers. So let's look at the table a bit more closely. So we can see if both of them are 0, right, only then we get a 1. In OR gate, when both of the inputs are 0, we're supposed to get a 0, right? But it's the exact opposite of it. So instead of a 0, we actually get a 1. So even if we have a 0 and a 1, we still get a 0. So basically we can say in A or B, even if there's 1, just only 1, then we'll get 0 because it's gonna be flipped. So we can see right here the NOR gate is the combination of OR gate followed by a NOT gate and outputs high signal 1 only both of the inputs are 0. So only both of the inputs are 0, then we get a 1. In all the other cases, we'll actually get zeros. And the symbol for NOR gate includes an OR gate. So this is exactly just like the OR gate, right? There's no difference. This is the OR gate, a curvature, but the key difference being this small circle right at the end of the output that indicates the negation. So next one we actually have the XOR gate. So this is the XOR gate, short for exclusive OR. It's a bit different. It only gives 1 when exactly one of the input is 1. If both inputs are the same, then the output is 0. This makes it really useful in things like binary addition when you want to know if the inputs are different. The extra curve at the symbol is how you can tell it apart from a regular OR gate. So a regular OR gate looks like something like this, right? Yeah, but an XOR gate will actually have an extra curve just here. Okay, So let's take a close look at the table of the XOR gate. So we can see only when both of the inputs are different, right? So we have 0 here, 1 here, right? So both of them are different. We have 1 here and 0 here. Only when both of the inputs are different, then we get high outputs. So high here, high here. When both of the inputs are same, like we have 0 here and 0 here as well, so we'll actually get a 0. Just like here as well, we have 1 here and 1 here. So like above, we'll actually get a 0. So the XOR gate outputs a high signal 1 if only one of the inputs is high. So just like we say, this is another way of saying the exact same thing. So XOR outputs 1 only when one of the inputs are 1. So we can see this is 1 here, this is 1 here. So one of the inputs are only 1. That's the main thing, only 1. So we have 1 here and 1 here. So the output is going to be 1. So next we have the symbol. Like we discussed, the symbol actually looks just like an OR gate with one exception, and that's there's another curvature. And this is a boolean function for the XOR gate. So first we have a prime b, then a plus, then a b prime, right? So both of them are different. So first we have prime in a, and in the second one we have prime in b. So there's another way to write this function. So this is the simplified version of a prime b plus a b prime. So we can just write it like this. Yeah, this is the logo, the sign for XOR. Then we actually have an XNOR. So finally XNOR, the complement of XOR. So this one gives 1 when both inputs are the same. So 0 and 0 or 1 and 1, then we get the output high. So both of them has to be the same. It's used in circuits where you need to check if two values match, like comparators, its symbol is just like XOR but with a bubble at the end. So it looks exactly like an XOR gate, right? We have an extra curvature right here and AND gate right here, but the key difference being we actually have one small circle just at the right side near to the output. So the XOR gates are outputs a high signal if both inputs are the same. So we can see when both of them are same. So we actually have two zeros here, right? Then we will actually get 1. We have two ones here, right? Then we will actually get an 1. And we do not have the same inputs here. So one is 0, another one is 1. So these are two different inputs. So what will we get? We'll actually get a 0. And the same here as well. So we have 1 here and 0 here. So both of them are different. So we'll actually get a 0. So now that we have actually discussed about the logic gates, how they look, and the truth tables, let's actually look over the applications of these logic gates. So here are some common uses for logic gates. In digital logic circuits, they are everywhere. CPUs, memory, and so on. We also use them to simplify Boolean expressions when designing logic. And logic gates like NAND and NOR are especially important because we can build things like latches and flip-flops with them, which are the foundation of memory and storage. So logic gates are used to design circuits in computers, smartphones, and other digital devices, serving as the foundation of arithmetic and control operations. Boolean algebra. Logic gates model Boolean expressions, allowing simplification and optimization of complex logical functions. So with the use of logic gates, we can actually simplify a lot of Boolean functions. That's very useful. And memory devices. They play a crucial role in creating memory storage devices like flip flops, which are essential for storing binary data. So let's go to the summary and the conclusion of logic gates. To wrap it up, logic gate all the logic gates we just went over, and or not, NAND, NOR, XOR, XNOR, are the basics behind how digital systems make decisions. Understanding how they behave, especially through the truth tables, is the key to moving on to more advanced stuff like designing adders or memory elements. That's pretty much. So logic gates are essential elements in digital look to carry out fundamental logical functions, grasping their behavior and truth tables. It is vital for crafting intricate circuits, right? Like we discussed. The utilization of these gates reaches far beyond basic circuits, impacting sophisticated technology in computing and telecommunications. So fundamental components. Logic gates perform basic logical functions in digital electronics. Knowing the behavior and truth table is crucial for circuit design. Applications in and technology. They use a, their use extends to advanced computing and communication systems. That's pretty much it for the overview. Thanks for checking out. Have a good day. Take care.